Hi, my name is Guokan Shang. The topic I'm going to talk about in this video is energy-based self-attentive learning of abstractive communities for spoken language understanding. This is joint work with Antoine Tixier, Mihaly Svazizhanis, and Jean-Pierre Lohe. We are from the academic and industry sectors, École Polytechnique and Dina-Gora in France, and Athens University of Economics and Business in Greece. Let's start by looking at the task of abstractive summarization of conversations, which aims to take a transcription as input and generate an abstractive summary as output. Previous work decomposes it into two subtasks. As shown in the figure, given a transcription on the left, the goal of subtask A, or Abstractive Community Detection, ACD, is to group utterances according to whether they can be jointly summarized by a common abstractive sentence. Such groups are called abstractive communities. Here we have 4 of them corresponding to 4 colors. Once they are obtained, a sentence is generated for each group by subtask B, thus forming the final abstractive summary on the right. We argue that ACD should be broken down into 2 steps. Step A1 extracts important or summary-worthy utterances. Step A2 groups extracted ones into communities. This A1, A2, B process is more consistent with the way humans treat the task. For instance, let's look at the human annotations from the AMI meeting corpus. Successive green nodes on the left denote utterances in the transcription, while black nodes correspond to the extracted ones that are judged important. Then they are grouped into 4 communities, each of which is jointly summarized by a sentence from the abstractive summary, shown on the right. In other words, the former convey or support the information in the latter. So finding black nodes corresponds to step A1 in our pipeline. Step A2 groups them into communities, and step B generates 1 sentence for each community. We note that the steps A1 and B have been extensively studied as extractive summarization and generation problems, while step A2 utterance clustering is a task little explored in the literature. So our work focuses on this step in particular. Previous work performed ACD either in a supervised or unsupervised way. They either train multiple models on different labeled datasets and heavily rely on handcrafted features, or are incapable of capturing the complicated structure. In our work, we first introduce a non-contextual utterance encoder. We then train it using the Siamese and triplet energy-based architectures, whose objective is to project utterances into an embedding space in which the ones from a given community are close to each other. Finally, we apply a clustering algorithm on the trained embeddings to get communities. Let's start with the Siamese architecture. It takes as input pairs of objects. The input X and Y are passed through the same encoder GW. The output embeddings are then compared with the distance measure D. The training objective consists in minimizing the output scalar energies associated with positive pairs and maximizing those associated with negative pairs. Here, the energies are distances in the embedding space. In our case, a pair is positive if X and Y belong to the same community. Otherwise, it is a negative pair. Triplet architecture is a direct extension of the Siamese one. It takes as input triplets X, Y, Z, referred to as positive, anchor, and negative respectively. The training objective is jointly minimize the positive anchor energy and maximize the anchor negative energy. In our case, positive and anchor items are utterances from the same community, while negative item is taken from any other community. Now let's move on to our contextual utterance encoder. It consists of 3 components: The first one is the word encoder as shown in the upper right corner, used to combine the word-to-vec vector with the discourse features into enriched word representations. The second component, utterance encoder, is shown in the center. For the target utterance UT, we feed the BiGRU layer with a sequence of word representations for all words U1 to UN, prepended and appended with two context vectors UPre and UPost. We then pass the BiGRU notations to a basic self-attention mechanism and a dense layer. The final embedding of the target utterance is used in the Siamese and triplet architectures for distance comparisons. Next, pre- and post-context encoders have the same architecture, so I'll only present the pre-context one here. It is used to aggregate UT-1 to UT-C preceding utterances into a context vector UPre. C is the context size. Our context encoder has two levels. At level 1, the same attention mechanism alpha is applied to all utterances separately in order to combine the word representations into an utterance representation. This mechanism is same as the previous one, except there is an extra input that consists of the element-wise sum of the word representations of the current utterance UT. We hope that by letting the mechanism know about the content of the current utterance UT, it will be able to extract complementary rather than redundant information from its contexts, and thus produce a richer embedding. In the end, because there is a strong time dependence between utterances, in other words, the context utterances that are more close to UT are more related or important to UT. Thus, at level 2, we use a time-aware self-attention mechanism to aggregate utterance representations obtained at level 1. It combines three parameterized time decay functions, convex, linear, and concave, into a universal time decay function, innovated some way. The three functions assume the strength of dependence to weaken rapidly, linearly, and slowly as the distance in time increases. To sum up, our model makes use of three different self-attention mechanisms. Once our encoder has been trained within the Siamese or triplet architecture, it is used to project test utterances into an embedding space. Since communities can overlap, we use a probabilistic version of k-means, the fuzzy c-means applied to the learned embedding space, which returns a probability distribution over all communities for each utterance. We experiment on the AMI meeting corpus. We evaluate our encoder and four variants against two baseline encoder, LD and Han. LD is a sequential sentence encoder. Han is a hierarchical self-attentive network. We compare our full pipeline against supervised systems based on TF-EDF and word-to-vec features, and LCSEG, which is a topic segmenter used in the previous works. For the supervised systems, we use an approach similar to that of Murray and al. More precisely, an utterance graph is created, whose edges represent if or not two utterances are jointly summarizable. Finally, an overlapping community detection algorithm, Conga, is applied to the graph. For the evaluation, we first test whether the distance in the final embedding space is meaningful. To do so, for a given query utterance, we rank all other utterances in decreasing order of similarity with the query. We then use precision recall and F1 score at k to evaluate the quality of the ranking. We use a fixed k equals to 10 and a variable k equals to v. We evaluate our clustering results using the omega index, a standard metric for comparing non-disjunct clustering, used in the ACD literature. Again, we use a fixed number of clusters equals to 11 and a variable one equals to v, supposing the number of clusters is known for each test meeting. We tried different context sizes on the validation set under two settings, with pre-context only and with pre plus post contexts. Results clearly show that the second one is much better than the first one, and increasing C always brings improvement with diminishing returns. We select 1111 as our best context sizes. Results on the test sets averaged over 10 runs are shown in this table. Based on rows A1 to A3 to F1 to F3, our model using best context sizes 1111 outperform the ones using reduced 30 and no context 00, both for Siamese and triplet. This confirms the value added by our context encoder. When comparing with variants of our encoder, for Siamese, our model outperforms its two variants for all metrics. However, under triplet configuration, the CAS variant is better, in which we replace the time-aware self-attention with basic self-attention. Overall, our encoder and its variants outperform the Han and LD baseline encoders, and our energy-based approach significantly outperforms all supervised and unsupervised baseline systems. Now I'd like to move on to the attention visualization part. Given the target utterance highlighted by the black frame, and the rubber case requires rubber buttons, so if we definitely want plastic buttons, we shouldn't have a rubber case. And it's 11 pre and 11 post context utterances. The content-aware self-attention in gray color focuses on the informative and complementary words in the context that are central to understanding the target one, such as custom design, material, recommend, titanium, wood, and so on. The time-aware self-attention in blue color places more importance over the context utterances that are close to UT. It is interesting to observe that distributions are not symmetric. Also, only the utterances immediately follow UT seem to matter, while the attention weights are much more uniform across the preceding utterances. The self-attention in red color focuses mainly on the special pre-context token pre, meaning that pre-context is much more important than the post-context here. It is also interesting to note that considerable attention is being paid to punctuation marks. This makes sense since they are important pieces of information for utterance type, such as statement or question. To summarize, the results show that the three self-attention mechanisms of our model are able to adaptively focus on different information in order to cooperatively produce a meaningful representation. Well, that brings us to the end of my presentation. Now, I'd like to summarize our main contributions. Firstly, we formalized the ACD, a crucial subtask for abstractive summarization of conversations. The AMI corpus preprocessed for this task, and the code are publicly available to foster research on this topic. Secondly, we proposed an energy-based learning approach to this task, using Siamese and triplet architectures to learn utterance embeddings for clustering. And finally, we introduced a novel utterance encoder featuring three types of self-attention mechanism and taking contextual and temporal information into account. Future research should be devoted to, first, evaluate our approach within the full abstractive summarization pipeline, A1, A2, and B. Second, apply our contextual utterance encoder to other tasks, such as dialogue act classification. This work was supported by the Link2 Meeting Assistant project. And thank you for your attention.